and principal component analysis into more interesting regimes in latent factor models and non-negative matrix factorization. But first, I wanted to just make a quick announcement that as I announced on Piazza, lecture next Thursday is canceled because of the AI for Science workshop. Anyone here is welcome to attend the workshop. Of course, if you want to have your name accounted for over lunch, please RSVP. The RSVP link is right there. It's also on the Piazza post that I made a couple days ago. And we have a great lineup of speakers, from people doing deep learning for chemistry and biology to brain-computer interfaces, robotics, including an external speaker from NVIDIA Robotics, and various forms of experiment design in protein engineering, nanophotonics, clinical therapy, and many other topics as well. And it'll be in the Beckman Auditorium next Thursday. OK. So today, we'll start with just a review of some useful matrix properties. And then we'll go on to latent factor models and non-negative matrix factorization. So just to recap, an orthogonal matrix, U, for now, assume it's U is a squared matrix, D by D, where D is the dimensionality of your data. A matrix U is orthogonal if U transpose is equal to the identity, and if U transpose U is equal to the identity. What that implies is that for any individual column of U transpose U is 1, which means that it's a unit vector. And for any two separate columns, U and U prime, they are orthogonal to each other, which means that their inner product is 0. What this also implies is that U is a rotation matrix, and that U transpose is the inverse rotation. So if we rotate X by applying U transpose X to it to get X prime, then we can reverse that rotation and get X back by multiplying X prime with U. We can project a data point down to a low-dimensional subspace by taking some columns of U, let's say the first k columns in this example, and multiplying it to X to get a new representation X prime. And we could treat the columns of U, the first k columns of U, as the new axes of this representation. If we think of the identity, for example, the representation would just be, that the new axis would just be the basis vectors along the original axes, if U was the identity matrix, for example. And we could, of course, reverse that projection and look at where the data points live in the original high-dimensional space by simply reverse multiplying by U. And so, pictorially, what that looks like, if you go from 2 to 1 dimensions, is that this is your 2-dimensional data, and these are your axes defined by U. Then we can project down to 1 dimension by multiplying, let's say, the first column of U, U1, with all your data points. And then we can recover where those data points in this projection live in the original representation of the space. So back rotate by multiplying by U1. So the singular value decomposition, if we take the matrix X, capital X, as a matrix where each column of X is a data point, then we can compute the singular value decomposition as follows, or represent the singular value decomposition as follows. It is the matrix X is equal to U sigma V transpose, where U and V are orthogonal matrices, and sigma is a diagonal matrix. And one of the properties of the singular value decomposition is that the U's are ordered such that the first k columns of U is the k-dimensional subspace of the full dimensional space that captures most of the variability of your data matrix X. What that means is that it is the k-dimensional subspace that minimizes the residual of the reconstruction error. And so this is the reconstruction error. If I project each data point X down to this k-dimensional subspace and then try to recover what it looks like, which is basically what this looks like, if I were to project all this data onto a one-dimensional subspace and then recover what it looks like, what is the reconstruction error of this versus the original data? What is the squared error, in other words, between these data points and these data points? And the first k columns of U for any number k is the k-dimensional subspace with the smallest such residual. Or in other words, the best k-dimensional reconstruction. And PCA, which stands for Principal Component Analysis, is closely related to the SVD. In fact, in the examples that we talk about, they're essentially equivalent. In PCA, we operate on XX transpose, which is a D by D matrix. And the way that you could see the equivalence is that if you look at XX transpose and you compute and you write it out in its SVD formulation, and because of manipulations of geometric and linear algebraic operators, and the fact that V transpose V is the identity matrix because it's an orthogonal matrix, then you get back this, which looks exactly like the PCA. In fact, this lambda, diagonal lambda matrix is exactly sigma squared. Any questions on that so far? This should just be recap at this point. Okay, so we spent a bit of time in the previous lecture talking about eigenfaces as a one grounded example to think about applications of these types of unsupervised learning techniques. In eigenfaces, each column of U is, and I should mention that we did a few modifications to get U prime and V prime because we had to get rid of this, we wanted to get rid of this sigma squared, so we just, or sigma. So we just put part of it in U and part of it in V to get U prime and V prime. We covered this in the previous lecture. And so now every U prime is an eigenface, so it's a basis face. And then V prime is the coefficients of a particular, in this case, CS155 student, and how they are represented as a linear combination of these eigenfaces or basis faces. Okay, so we talked a lot about norms in this class, especially in the first couple of weeks. And if we can extend these notions of norms on vectors to matrices as well. Some things change, but many of the intuitions stay the same. And the two norms that are relevant in this class are the Frobenius norm and the trace norm. So the Frobenius norm of a matrix is the square root of the sum of the squared of the values of that matrix. So I and j here index over the two dimensions of the matrix, and we take the sum of squares, and then we take the square root. It turns out, and we'll see this in a couple of slides, that this is equal to the sum of the squares of the singular values, which is equal to the sum of the eigenvalues. And then you put it under a square root. The trace norm is equal to the sum of the singular values, and it's, as we'll see, is equal to the trace of the square root of x transpose x. So these decompositions, singular, the SVD and the PCA decompositions, capture something about the norms of these matrices. So let's look at the Frobenius norm. Another way to write out the Frobenius norm is as what's called the matrix inner product. The matrix inner product is simply the trace of x transpose x. So if we wanted to compute the matrix inner product of two matrices, we would compute the trace of one matrix transpose times the other matrix. And if we take the two norm in a vector notation if we take the two norm of a vector, we would simply compute that vector transpose with itself, or excuse me, the squared two norm. And so the trace here is in a matrix inner product, we have to take the trace. And so if we write this out as the singular value decomposition of x, we get the trace plus it's the singular value decomposition representation. We do some manipulations, and we get this back. And this middle equality is based on the trace rotation equality. This is just a known fact about trace the transpose V is the identity, we get back this, and this is a diagonal matrix. So the trace of a diagonal matrix is the trace is the sum of the diagonals. So you get the sum of the squares of the singular values. For the trace norm, you can write it out as the trace of the square root of the matrix multiplied with itself. Again, we replace the matrix X with its singular value decomposition, and we get something that looks like this. again, VV transpose is the identity matrix, so we get back, we can simplify down to the sum of the singular values. And the only difference between these two is whether or not we take the square root inside the trace. Yes?
Could you explain the last step of the second one?
This one?
Yeah.
So V is norm preserving. There's on the link to the course website, there's like a list of matrix identities. There's nothing special going on here. It's just we're just invoking matrix identities.
I'm wondering, is that true in general?
It's not true in general. Yeah, it's true for trace and for orthogonal matrices. Okay. Yeah. So you can think of the Frobenius norm as the squared, as the matrix version of the L2 norm. In the L2 norm, we compute the square root of the sum of squares of each entries of the vector. In the squared Frobenius norm, we compute the sum of squares of every entry in the matrix, which, by the way, is equivalent to the sum of the squares of the singular values of that matrix. So if we want to use, if we want to regularize, if we have a model where the parameters of that model is a matrix rather than a vector, and we'll look at some examples in later on in this class, then if we wanted to, let's say, regularize the parameters, which is matrix structured rather than vector structured, then we may want to regularize using the Frobenius norm. Okay. I'm next going to talk about the Frobenius norm, or excuse me, the trace norm. But before I do that, I wanted to just touch back on sparsity. So recall in homework 2 that we spent some time thinking about L1 and sparsity. And L1 is the regularization where we simply sum the absolute values of the entries of a matrix. And we made the observation that L1 regularization induces sparsity. Now, of course, we don't try to directly regularize for sparsity, which would be something like the L0 quote-unquote norm, which is not, it's not actually a norm. And the reason why we don't regularize to L0 is because the L0 norm is flat or discontinuous everywhere. So it's hard to optimize. And L1 induces sparsity in a way that is much easier to optimize. So the trace norm, you can think of it as an analog to sparsity, but not of the non-zero entries of a vector, but of the rank of the matrix. So matrix X is considered low rank if it has very few non-zero singular values. In other words, the rank of a matrix is equal to the number of singular values that are greater than 0. This is, again, a flat or discontinuous function, so you wouldn't necessarily want to regularize using this function. And the trace norm, as you can see, is simply the sum of the singular values. Now, the singular values are guaranteed to be non-negative, so I don't have to take an absolute value. But you can see that there's a direct analogy to inducing sparsity, not in the individual weights, but in the rank of the matrix. And this is also known as spectral sparsity by some communities. And we'll see in some examples why you might want to do this. Yes?
So when you do PCA on some kind of real data that has some noise, do you ever get singular values that are 0, or no, they just get smaller?
PCA?
Yeah, or SVD.
With noise.
Yeah.
If you have if you have generic noise, typically you never get singular values that go to 0. Yeah. Yeah, because the noise is typically full dimensional. Yeah. Of course, if you make strong assumptions about the bound on the noise, then you can set your regularization such that if the weights, if the singular value fluctuates in some small number, I could by doing trace norm regularization, you could clamp that down to 0. Just like an L1 regularization, if the weights sort of wobble around, you can increase the L1 regularizer and clamp that down to 0. Yeah. Joel Trop and Babak Hasibi, who are professors here at Caltech, have spent years studying this. And so if you're interested in all the nitty-gritty details, I recommend you look at their websites and the papers they published. Yeah. OK, so a few other properties that are useful, may be useful on homework 5 after the Kaggle competition, include things like the Cauchy-Schwarz inequality for matrices, the arithmetic mean, geometric mean inequalities, the fact that, we've talked about this before, that these orthogonal matrices are norm preserving, and if A is a square diagonal matrix, then the trace norm is actually equal just to the sum of the diagonals. OK, so just to recap, we talked about in the bulk of the previous lecture, we talked about the singular value decomposition and its applications. Basically, for all intents and purposes in this class, it's mathematically equivalent to the principal component analysis. And the reason why we care about the SVD is that we care about finding low-dimensional projections of the data that are good reconstructions of the data. In particular, that means the first k columns of the U matrix from the singular value decomposition. Just one slide summary of what we talked about in the previous lecture. Any questions up until this point? OK. Let's talk about latent factor models. So to motivate the latent factor model paradigm, let's first talk about a classic problem known as the Netflix problem. So we have a matrix Y that is ordered by users by movies. So we have capital M users and capital N movies. And Yij is the rating, let's say 1 to 5, 0 to 1, whatever the scale is, that user I gives to movie J. And we want to find a low-dimensional U and V. So you can think of these as a user factor and a user factor and a movie factor, such that we have basically a linear function that predicts for any given movie what this user would like, and for any given user what the movies they like, that approximates this matrix. In other words, we want to find a low-dimensional U for every user and a low-dimensional V for every movie, so that if we have a linear inner product function between the two, it's a good regression. It's a good regression estimate of the rating this user would give this movie, minimizing the square square distance between Yij and Ui transpose Vj. This is exactly like the SVD. And in fact, in certain cases of this problem, you can actually exactly solve this using the SVD. And any examples that look like this. So this is a visualization of 2 dimensions, the top 2 dimensions of V. So this is the top 2 dimensions of V. Hold on. Let me make sure I get my. Yeah, V is the movies, U is the users. Yes. So you see that there are movies that are, like a movie like Braveheart is sort of on the top right corner of this 2-dimensional representation. And the authors of this paper that created this visualization, they sort of took a look at this visualization and they assigned some meaning to the axes after post-visualization. So the meaning that they assign include things like serious versus escapist, and geared toward males versus geared towards females. May or may not be the best meanings that they assign, but these are the type of exercises you can do with these low-dimensional representations. Okay, so what is the actual Netflix problem? Why can't we just directly use the SVD? The actual Netflix problem is the primary issue is that Y is not a completely filled matrix. Y has missing values. And in fact, the Netflix problem itself is kind of silly in some sense if Y was completely filled out. Because why does Netflix care about this problem? They care about this problem because they want to know what other movies you might like that you haven't seen yet. Right? They want to estimate, based on the movies that you've already rated, what other movies you might like. That's one of the reasons why they wanted to solve this problem in the first place. If Y was completely filled out, we could simply call the SVD. End of story, we're done for the simple version of the problem. So the primary thing we're going to talk about in latent factor models for the next bulk of time is the fact that Y has missing values. This is the problem known as collaborative filtering. So this is the formal problem definition of which the Netflix problem is an instance of. So we have M users and items. They don't have to be users and items, but typically these problems are cast in the context of recommender systems. A subset of the user-item pairs have ratings of some kind, and most are missing. And the goal is to predict the missing values. So this is the latent factor formulation for the collaborative filtering problem. We only have labels and no features. So it's kind of in some sense, kind of an inverse of the unsupervised learning problem, of the traditional unsupervised learning problem. We want to learn a latent representation over users and movies such that we minimize this error. So on the right, this is your standard regression error for the user item ratings that we do observe. This is if we knew what V was, if we had a feature representation for every item, then this is a simple linear regression problem. If we knew what U was, if we had a feature representation for every user, then this is a simple linear regression problem on the movie side. And it turns out we actually have neither to begin with. We have neither the user vector models or the movie vector models, and we could treat either one as the feature and the other model, or vice versa. The problem is actually, in some sense, completely symmetric in its interpretation. And we want to jointly learn both simultaneously while minimizing this regression error, which is essentially the reconstruction error. And of course, we're going to do some regularization. So that's what this is. Any questions? Yes?
In the summation, so some of the a lot of the y values are missing.
Right. So I left the summation a little bit vague. Typically, it's only summed over the non-missing values. Okay. So I want to just highlight a connection to the trace norm. Suppose that we consider we're looking over all U and V that achieve perfect reconstruction. So in other words, we're only looking at U and V such that Y equals UV transposed. And now we want to find the U and V that has the lowest complexity under this complexity measure. which is basically just L2 regularization on U and V in the matrix case. So it turns out that this is equal to the trace norm of y. So if y has low trace norm, which also implies that it has low rank, so then the trace norm of y is equal to the U and V that achieves a perfect reconstruction of y that has the lowest sum of squared Frobenius norms. Here's the proof in one direction, the easier direction, just so you can see how we can use some of the ideas that we talked about in the beginning of, some of the identities we talked about in the beginning of lecture to sort of prove one of these, prove some of these properties. So the full proof is, of course, you prove both equalities in both directions, inequalities in both directions. And then we'll assume that we have the SVD representation of y. Okay. So to prove one direction, we we simply show that there exists a and b that is less than or equal to this guy, and therefore the minimizer must be less than or equal to this guy. And so we choose a and b equal to this, just like in the eigenfaces example. And then what follows is some fairly standard stuff. So the minimizer must be less than or equal to this, which our choice. Also, it's clear to see that. Sorry, I changed the notation A and B because U and V are typically used for to denote the U and V matrices in the SVD. But as you can see here, there's a clear relationship here. So first of all, it's clear to see that AB transpose equals Y by definition, basically. And so the first inequality is basically saying that the minimizer of this is less than or equal to this, which is basically also by definition. And then here we invoke the definition of the trace of the Frobenius norm, which is the trace of these guys. We apply the fact that, sorry, we apply the distributive rule. So we actually distribute. UU transpose and VV transpose are identity matrices. We get back this, which equals this. So the interesting thing is that, okay, if this A and B are not full rank, they're low rank. Let's say they're only k-dimensional. They're not. They only exist in a k-dimensional subspace of the full space. Then then Y must be also low rank k, and therefore the variability of users and how they like movies and how they're liked by users live in this k-dimensional subspace. And that's the k-dimensional representation we want to extract from the collaborative filtering problem. So in other words, this objective is highly related to finding the best low-rank approximation that approximates Y. Recall that the trace norm is similar to the L1 norm, but on the rank of the matrix rather than the number of non-zero entries. And so these two objectives are equivalent when the true rank. So these two answers are equivalent when the solution to this guy has the same rank as the rank you choose for these guys. So recall that here I choose k up front. Here I'm choosing k up front. And here I don't. The rank of this matrix is I don't control it in the very beginning. I get out an answer. If I happen to have guessed the same k of the rank of this guy when I solve this problem and force these guys to be rank k matrices, then these two will give you the exact same answer. But typically, people work with this formulation because it's more practical. OK, so I alluded to this before. I just want to touch on it again. There's a symmetry in this particular problem, right? We're doing linear regression, basically. Right? If we hold V fixed, we're doing linear regression on U. If we hold U fixed, we're doing linear regression on V. We could treat either as the model and either as the feature in linear regression. And we're basically learning both simultaneously and taking a more symmetric interpretation of both. So let's make sure this is running. Good, good. OK, any questions so far? OK, now let's talk a little bit about optimization. There's basically two ways to optimize. One is gradient descent, and one is alternating closed form optimization. And the way I wrote it here is just to make some of the notation easier to work with. There's nothing has changed other than if I sum over all possible ij, I need an omega term here that's either 0 or 1. 1 if I care about this entry, 0 if I don't. If it's missing, omega set to 0. If it's observed, omega set to 1. Otherwise, it's exactly the same. Sort of answers your question. So the gradient calculation, let's say I want to take the derivative or the gradient with respect to u sub I, right? Then this is the standard gradient you would expect from looking at homework 1, where we did gradient computation for least squares regression. And we all know that, at least for this type of least squares regression, linear least squares, where we hold V fixed, it has a closed form formula. So there's a few different options. We could take a single data point, and we could only update, the model parameters that are relevant for that data point. And what that means is, if we choose data point ij, then we'll take a gradient step for u sub I, and we'll take a gradient step for v sub j. And then we pick another ij, and we only update gradients for u sub I and v sub j. If we do mini batch, we have a mini batch of yij's, and we only update the gradients for the users and items that appear in that mini batch. You could also try to optimize for all of the data points relative to a single user at a time. So if I have user I want to look at all of the data points that user I has rated, and do a gradient update for all of it at a time. So you have different choices of how you can handle the scheduling of the optimization. The alternating optimization paradigm basically says, let's just solve the closed form solution for each ui or vj completely, holding everything else fixed. If I hold everything else fixed, this is a very simple linear regression problem, and I can compute the closed form formula. Of course, I have to invert this matrix. But that's what I can do. And I can just run a loop until I've appeared to converged. So I hope none of the examples of how to optimize for this problem are surprising. I mean, they're all fairly standard. There's just different trade-offs of how you actually schedule subroutines of the optimization problem. Do you just do the direct stochastic gradient descent? Do we do a stochastic gradient descent on an entire column of data at a time? Or do we try to solve one subproblem of this problem exactly while holding everything else fixed? So not surprisingly, alternating closed form optimization converges faster much faster in terms of number of iterations, but it requires inverting this matrix, which can be expensive. And so what people typically do is some kind of gradient descent for high dimensional or large problems. It also allows streaming the data. For smaller problems, I've often just done alternating closed form optimization, but for much larger problems, it's typically not possible. And so here's another visualization that the authors of this paper had in the paper. And by the way, this is the paper that won the Netflix challenge. And they won it using this latent factor model. And so what they're showing here is they centered the data points around the movie Wizard of Oz, and they looked at where other movies are relative to Wizard of Oz. So again, this is the V. These are the top 2 dimensions of the V matrix, which is the representation for the movies. So I think it's worth asking the question, why does this even work? We just have a bunch of Ys. We know some metadata that indexes the Ys. This Y was given by this user for this item. So we have some metadata about the Ys, and so that we can structure them into a matrix. We have literally 0 features. And yet we can construct, for example, let me just go back. Examples look like this. This one's maybe a cleaner example to look at, where there's something. It's not a super clean visualization, but you can see clear trends in that some of the movies over here are clearly more similar to each other than movies over here. Yeah. And why might we even expect that this is the case? Why might we expect to extract a V such that if we sort of plot out where the movies are based on their V coordinates, we get something that looks like this with this amount of coherence? Any guesses? Yes.
So if you're just like recommending movies to friends, you can look at how similar some person is to other people, and then look at what those other people like. It's like intuitively, that's like. And
okay, that's a great answer. Let me sort of help you fine tune that answer a little bit, neural network style, backpropagation style. So, what does similar mean?
So they have like similar ratings to movies that they
Okay, great. So users are similar if they like similar movies. What does it mean for movies to be similar?
I think they kind of have like the exact same thing.
Right. It's actually less. It's harder to think about in terms of words, but the actual definition is symmetric. Movies are similar if they're liked by similar users, by the same users. And so what that means is that there is a cluster of users that if they like Braveheart, they'll probably like Lethal Weapon, let's say, on average. That's more likely to be true than not. And so their weight vectors are going to be over here, where they have a high inner product with these movies. And so the whole thing is actually symmetric. And so the reason why we should expect this whole thing to work is that the metadata of the movies and users that index into this matrix creates this matrix that has low rank. If there are exactly 2 degrees of freedom in how users like movies, so which is, let's say this, if there are exactly 2 degrees of freedom to how users like movies, then this matrix has rank 2. And we could extract that out by setting k equals 2. And so the fact that we have users and movies liking multiple movies, even if it's not all the movies, and that we make this assumption that the similar users like similar movies and similar movies are liked by similar users, that is the assumption that allows us to actually extract these U's and V's despite the fact that we start off with just y's. So in other words, the way that people usually say this in more formal language is there exists a low-rank subspace of this matrix that captures all the variability of this matrix. Yes?
So a couple questions. How do you pick K?
Validation set.
Okay.
Yeah.
And then second, so in the two plots of the axes with movies on them you showed, the first plot has some labels to the axes that make some amount of sense. And then on the second plot, there's just some name feature. How do you get from some feature to giving you an actual real world name?
So you're talking about this one, right?
Yeah, so if you have got factor 1 and 2.
Right. So that's that. I mean, this is what you get in Python. You get factor number 1, or factor number 0, and factor number 1. Is right? Yeah. Yeah. These people probably use MATLAB. Okay. So how do you get that to the named feature? Yeah. Typically, it's through inspection. Yeah. Qualitative inspection. Yeah. Any other questions? Yes.
Yeah, if you've taken a group of Americans and shown them movies, they would have one set of rankings. You take a group of French people and show it, they'll have a different set of rankings. If you then combine them, does that mean you increase the dimensionality of the number of features you need to sort of map?
Typically, yes. So typically, so we'll touch on this in a more rigorous way, actually, at this point, or something related to this point towards the end of lecture, or later on in lecture. But yeah, typically, if you have like multiple populations of users, then you need to increase the rank. Yes.
If we take the case of like rankings of a movie, say it's like bounded like 0 to 10 or something like that, when you solve this optimization problem, are you guaranteed that you don't predict anything outside of those bounds? You might predict that somebody unobserved has like a ranking of 11.
A rating of 11.
Yeah.
Yeah, sure, that happens.
So do people like apply constraints and put a prior over those things? Is that useful in practice?
I don't think it's typically not done.
Like model your features or your ratings as some sort of a categorical distribution.
In modeling your features in a categorical distribution, you typically put a logistic transfer function on top of the raw score. Right, so the probability that your movie is in category 1 versus 2 or 3 is e to the score of category 1 divided by a sum of e to the score of category 1 plus e to the score of category 2 plus e to the score of category 3. That, like the sigmoid.
Right.
Yeah. In which case we're not constraining the raw score. The raw score, if you're 100% confident that you're in category 1, the raw score should be infinity for category 1 and negative infinity for categories 2 and 3, so on and so forth. That's the way people typically handle it. So yeah, so if you care about probabilities, what you would do is you would change the squared loss to a log loss, right? Yeah. What is the probability that this user will like this item? You would change the squared loss to a log loss. And then y would be either 0 or 1, let's say. Yes? It's a great question. Of course, it depends on a number of things that change all the time, like memory and size of your RAM and stuff like that. So I didn't want to put like a definitive number there because whatever number I put there will become outdated in like 5 years. I would say that these days, with the size of the data sets that we're dealing with, would dramatically outpace the size of how fast your RAM is growing, let's say. That gradient descent is the de facto thing that people use. Yeah. In practice. Like if you were to do an internship at, I don't know, YouTube for something like this, they typically just only do gradient descent, stochastic gradient descent. Things might change in the future. In 10 years, maybe someone might invent super cheap RAM, and who knows? But yeah. Any other questions? Yes.
What if this assumption doesn't hold true and don't find a low-rank subspace?
Okay, so I think perhaps the key word here is all the variability. In practice, people want to capture most of the variability. And I think that assumption is actually a pretty reasonable one for almost all applications. That the variability is concentrated in a lower dimensional way, and not in a all-dimensional way. If that is not true, then you shouldn't be doing this. But if you think about it, I mean, we spent a week on deep learning. What does deep learning do? Deep learning takes high-dimensional data and compresses down to hidden layers, and then compresses down to hidden layers in a nonlinear way. Deep learning does it in a nonlinear way, but there's a bottleneck in the number of hidden units. So, even in deep learning, which has advantages because it's a nonlinear function class, is internally doing compression of the data into some implicit low-dimensional subspace. Yeah. Yes.
So I guess just a follow-up question to that: can collaborative filtering be able to find nonlinear relationships?
It's a great question. Classical collaborative filtering, no. We will look at a few examples of nonlinear things that combine collaborative filtering type. I mean, okay. As will become clear in the next few slides, there are ways you can sort of extend collaborative filtering in latent factor models, and there are ways that we can blend that with things like deep learning. And perhaps your answer will become clear through all the information that I'll present in the rest of the lecture. Okay, so let me move on. So first I want to talk about an aside on multitask learning, which we talked about briefly a few weeks ago. So in multitask learning, and this is just one particular version of it, a relatively clean version simply for presentation purposes, we have M tasks. And for each of the tasks, we have, let's say we have the exact same labels, so xi. Excuse me, the exact same inputs xi. So for every task we've acquired a label, a target label, y sub I for the exact same xi. Of course, this assumption can be relaxed in practice, but it makes the math much more compact. And then we get something that looks like this, right? So we're minimizing squared error here for simplicity because squared error is the easiest loss function to reason over. You could do hinge loss, you can do log loss. It doesn't really change the story. It just makes the math a little bit less clean. The interesting thing here is the regularizer, right? We have this weight matrix W, which has each column of W is the weight vector for a single task. And so now we have a weight matrix, and we want to regularize it. So common examples of this are personalized recommender systems. You have these items with some features on it, X. We have different users with different preferences. Which item do I like? So on and so forth. So how do we regularize? Well, if we regularize, there should be a Frobenius norm here, right here. But if we regularize using the standard L2 version, matrix version of L2 norm, which is the squared Frobenius norm, then things completely decompose additively into independent tasks. We can solve for each task, W sub m, independently of each other. And so it makes no difference whether or not it's in this big giant optimization or we split it off and shard it off into independent optimization problems. So in other words, we're not really treating it as a multitask learning problem. We're just treating it as m different single task learning problems. But okay, how about we regularize the W matrix to have low trace norm. What does this mean? This means that if we take all the W vectors of all the different tasks and put it into a matrix, that matrix should have low rank. So the variability of different users that we estimate should do so in a low dimensional way. So just as I pointed out earlier, there's a relationship between the trace norm and this and the sum of square norms of U and V, where U and UV transpose is equal to the original matrix. So there's a relationship here. So what we can do is we can, taking the trace norm and the low rank assumption as a starting point, use this approach instead. Use this formulation instead, which is typically much more practical in practice. What does this mean? This means we want to find a U and V such that we minimize the loss of this guy. So we have our xi, and we multiply xi by v, and v is low rank, so vxi is lower dimensional than xi. And then we learn a low dimensional ui, which is a user-specific model. Or excuse me, I use m to denote users here. So if u and v are rank k, so they're k-dimensional matrices, then Vx projects down to an x prime, which is k-dimensional rather than d-dimensional. And we learn a k-dimensional model per task rather than a d-dimensional model per task. So why might this be something that's good? Well, in the original problem, if we treat everything as an independent task, in the original not multitask version of this problem, then we have d times n parameters that we need to estimate. In this version, we have d times k plus n times k parameters that we need to estimate. N times k is the V matrix, corresponds to the V matrix, and d times k corresponds to the V matrix, n times k corresponds to the number of users. And if k is much smaller than d and n, then this is there are fewer parameters in this model. So it's easier to estimate this model reliably because it's less complex. And this is great if the low rank assumption is a good one. If I have a bunch of different users or tasks, and the variability across those tasks, at least in terms of the model I'm trying to estimate, is low rank, then this is a good assumption to make. Now, this looks a lot like collaborative filtering. And in fact, it is, in some ways, an extension of collaborative filtering. Collaborative filtering is the special case where xi is an indicator basis function. So if xi is 1 in exactly 1 in exactly one entry and 0 everywhere else, then you get back the collaborative filtering problem that we talked about before. Another way to think about the difference is that we have no way of describing items, each item I, other than its identity. So the description, the feature vector that describes our items is equal to the number of items. That's what collaborative filtering is saying. Whereas if we have a feature vector that describes items, but we still want to make it a lower dimensional representation, then we could do it in this way. And of course, we could do general bilinear models. So we could actually have users, we could actually have features of users, I'll call those Z, as well as features of items. So I may, and I'm going to learn this U and V matrices that are sort of in some sense global. And so if I have a bunch of attributes about an individual user, that's fairly high dimensional. It could be anything. It could be age, gender, education level, zip code. It could be a super high dimensional representation of a user. And I could project that down to a low dimensional space. And that's what this looks like. And in the case where Z sub I, I know nothing about the user other than its identity, then Z sub I is just an indicator basis vector. Okay, so yeah, so this slide is basically a comparison of what kind of information you can assume you have, what kind of information you don't have. Do you have features of users, yes or no? Do you have features of items, yes or no? What is the what are the different trade-offs if you sort of try to model low dimensional projection? Right. If I have an F dimensional user feature vector, then this might be easier to learn than if I use the identity of the users, which is capital M. And so there's no single right answer here. This is just it depends on your application. Okay. In the interest of time, I'm running a little bit behind, so I'm going to skip ahead that summary slide. I just want to briefly touch on the idea of nonlinear projections. So as was asked earlier, these are all linear projections. What about nonlinear projections? So Vx is a linear mapping to a low dimensional space. We can also learn nonlinear mapping. So for example, instead of Vx, so imagine that we have a function that projects your raw data description of an item to some low dimensional space. If that function is linear, it looks like Vx. If that function is nonlinear, it's just some nonlinear function. I could, for example, take a deep neural net and then take the last layer of hidden layer of activations and have that be my low dimensional representation. And in fact, people do that for stuff like this. Right? So if I want to do something that looks like collaborative filtering for items that you can scrape from Amazon, you can get embeddings that look like this. And these are created by mapping from the images of these items using a neural net into some low dimensional representation, which is basically the last layer of hidden units of these neural nets. And I'll talk more about this application in a few weeks when we talk about more recent applications. But this is just a hint at what's possible. Okay, in the remaining time, I want to talk about non-negative matrix factorization. So some limitations of PCA and SVD. We're going to go back to linear now. Okay. I know everyone loves nonlinear deep learning stuff, but it's good to learn the linear stuff first. Yeah, actually, in many ways, the deep learning stuff isn't even that interesting in some sense, right? It's just a bunch of nonlinearities of basic stuff that you learned in the linear case. So you can deep learningify any of this stuff. But let's learn the linear version first. I don't even know that's a real word. Maybe I just invented it. Okay, so one of the limitations of PCA and SVD, well, there are many data sets where all the descriptions are of the data is non-negative, which is actually true in the image case for eigenfaces. And so you might get data points that look like this, right? Where the two bases, if you were to eyeball this is a 2D case, of course, it's simple to visualize 2D cases. But if you were to eyeball this example, it seems like the two bases, or the two ways I would summarize this data is, does this data point lie more closer to one of these two red axes or red vectors? Whereas PCA or SVD, basically, they try to find this purple solution, assuming you mean shift. And you could argue that for this type of data, finding the red solution as a way of describing the data is better than finding the purple solution. And that leads us to what's called non-negative matrix factorization. So we assume that y is completely non-negative, and we want to find a non-negative u and v that approximates y well. And so we could do this for faces and other images, where this could be the pixel values at different pixels and people, and you get something that looks like this. And now I'm using the actual. So each of these is the actual face basis. I don't have to do some weird shifting to actually visualize things because none of the values are negative. It's important to keep in mind that the default face, if it's 0, if you have 0 coefficients everywhere, is completely black. The default image is completely black, so all zeros. And then we just add non-negative multiples of these guys to it. This is in contrast to the SVD solution, eigenfaces, that we saw before, where in order to even visualize these eigenfaces, I had to do some tricks to even visualize it. So recall that light means positive and dark means negative, and 0 actually is a gray values. So one of the things that comes up is that when you do this non-negative matrix factorization, you don't get orthogonal matrices. The columns of this U and V, or I call this A and B, are no longer orthogonal to each other. And so in order to invert things, you have to use what's called a pseudo-inverse. The objective function is very similar to before. We have for every entry ij that we observe, we have the target, and then U transpose V, and we have some loss function. And the reason why you might want to use non-negative matrix factorization is if you want your recovered latent factors, your bases that you recover, to all be non-negative. This is true for faces and any kind of image, and this is true for many, many applications. PCA and SVD will find the best orthogonal bases, and because it's orthogonal, it has to be negative. You can only have a single basis that lives in the all positive quadrant or orthant. Everything else has to have some negative component to it. And one of the things is that non-negative matrix factorization is often, the bases are often easier to visualize. Now, what you see is literally what it is. And this is true for many applications where a negative value doesn't even make sense for your application. Like, what does a negative pixel value mean? Of course, by virtue of PCA and SVD finding orthogonal bases, you can find better reconstructions with fewer bases. And so you typically require more bases in non-negative matrix factorization, so a higher rank solution, in order to get a good reconstruction. And I just wrote here just a general case where we have features on z and x of the two dimensions instead of just the y, but otherwise it looks exactly the same. Okay, I want to conclude with another example. I think this one's pretty fun. It's more fun if you like basketball, less fun if you don't, but I think it's kind of interesting nonetheless. So this is a project that I worked on a few years ago where we're trying to recover a set of bases that describes behavior of people on the basketball court. The data was collected from the National Basketball Association. This study was done in 2013, so about 5 years ago. Who here follows basketball? Okay, so 3 people will think this is fun, and everyone else will think this is mildly interesting, possibly mildly boring. Anyways, so Tim Duncan was a very famous basketball player, still is very famous, recently retired, and we sort of looked at how where Tim Duncan likes to shoot the basketball, and so we found this heat map of where Tim Duncan likes to shoot the basketball. Darker means more likely to shoot, and this is a discretization of the cell. The challenge that we faced in this problem is that while Tim Duncan has a lot of playing time because he's a superstar, most players in the NBA don't play that much. And so we have, in some sense, a missing value problem or a low frequency of data problem. And so we did what you might expect. We trained a latent factor model. And this latent factor model, D is the number of locations on the court. So we discretized the court into little cells. And M is the number of players in the NBA, so 457 in 2013. And then we did this matrix factorization. This is non-negative. And we kept the rank at 10 in this example. And so this is the visualization of the L factor. And you could think of these as the archetypical shooting positions of where the players like to shoot the basketball. And then every player's shooting profile is a non-negative linear combination of these 10 archetypes. That's what the K numbers that describe every player is. And so here are some of the profiles you get as non-negative combinations of these, and each of these players are now described by exactly 10 numbers. Right, so this is the training data. 630 games from the NBA, 2012-2013 season. And you could even use this to make predictions. So now this is an actual application where we're combining multiple things that we've talked about in this class. We want to do prediction, like the probability of shooting a ball, logistic regression. We want to find the model for multiple players at the same time. So it's multitask learning. And we're going to invoke the low rank assumption in order to learn over multiple players more efficiently from a data efficiency point of view. I have a short demo. So this is the probability. Oops. This is the probability of this player, who is the ball handler, passing the ball, the relative probability of passing the ball or shooting the basket as a function of the location of the other players, location of that player, and yeah, the location of the defenders. So I could set this guy as the ball handler, and so on and so forth. So you can do stuff like this. Yes?
Is this also using the data on the players that you have? Like, are the probabilities different depending on which player?
Yeah, the probabilities are different. So much more likely to shoot the ball than him. I think he's the most likely to shoot the ball from far away. Yeah. So notice how there's a discontinuity because you're more likely to shoot behind the 3-point line than just inside the 3-point line. Okay, I'm running a little bit behind schedule, I think. Anyways, you can find the paper on my website and the demo on my website. And so in this formula I'm going to present to you, I'm just showing how different things can get combined. So we're going to predict the probability that given the certain state representation on the basketball court, the ball handler will shoot the basketball. What is that probability? And so this is just the standard log linear logistic regression formulation. It looks a little bit more complicated, but it just boils down to that. The thing that's interesting is that my scoring function, right? This is the raw scoring. So it's e to your raw scoring function, and rather in standard logistic regression, your raw scoring function is a linear score of the features. But here, the raw scoring function is going to be a little bit more complicated. In particular, the raw scoring function is actually a matrix parameter where I could index into that matrix depending on the player ID. So this is a multi-task logistic regression function where each task is a player in some sense. And I want to be able to estimate this model well for all the players instead of just the popular ones, despite the fact that most players haven't played well. And I'm going to make the assumption that if you, for example, if you tend to shoot a three-point shot in the corner, you'll probably shoot the three-point shot in the other corner because the most popular players do that. So again, like in the collaborative filtering, similar users will like similar movies. Here it's basically saying similar types of shooting players and how they shoot will shoot from similar locations. And that low rank assumption allows us to share statistical strength across players. So this is now log loss, and there's a there we go. That's the actual model. This is log loss, and I split this into a low rank decomposition, and I also have a bias term, which is do nothing, and then I do this minimization problem. So this is a simplified version, but essentially captures the essence of the model that we trained. We also forced that B and L be non-negative, so that you can have that non-negative visualization. You could do some gradients. You can compute the gradient the standard way. You have be a little bit careful with making sure you compute the gradient properly, but there's nothing magical or hard here. You just have to make sure you do it the right way. And in the actual formulation, we could do more than just we can do more than just predict the probability of shooting the ball. We could predict the probability of passing. Like, is this player more likely to? What's the probability of this player choosing to shoot the ball in this situation versus passing the ball? And it also accounts for where players are likely to receive passes from. So this part of the model says a player likes to receive a pass in one of these locations. And then where players receive passes from is a linear combination of these guys. Non-negative linear combination. You can model things that are player independent. So I could choose to index or not index things as I please depending on my modeling assumptions. So I also wanted a model where where passes tend to flow on the court in a model that's independent of the player ID. So if you're passing if the ball handler is passing from this location, the ball handler tends to pass to one of these two locations. If the ball handler is passing from this location, the ball handler tends to pass to one of these two locations. If the ball handler is passing from this location, the ball handler tends to pass to this location, and so on and so forth. Yeah. Right, so here I'm visualizing, so these are the latent factors, and any individual location activates these latent factors at two differing amounts. And so for this particular location, this is where this specific location tends to pass to. This is where this specific location tends to pass to, and this is where this specific location tends to receive passes from. Okay, the last thing I want to touch, just last 1 or 2 slides, is tensors. So a matrix is a 2D object. It's basically think of an array. A tensor is a multi-dimensional array. Here I'm showing you a third-order tensor. A second-order tensor is a matrix. So we could do tensor factorization in addition to matrix factorization. And this leads to things like trilinear models rather than bilinear models. So for example, we could have a user with a profile Z, an item with a description X, and a query with query words Q. And I want to estimate a model that can sort of learn this type of, I want to be able to learn this type of model in a way that's statistically tractable with very few parameters. So I'm going to make an assumption that things vary in a low-dimensional subspace in this third-order, 3-dimensional tensor object. Okay, so just to summarize, today we spent a lot of time looking at different versions of latent factor models, including its non-negative variants, can tolerate missing values. It's based on this assumption that there's a common set of tasks that are related to each other, and there's a low-dimensional variability between those tasks. And this is widely used in the industry. Latent factor models are one of the most popular things people use in industry. Any questions in the remaining 1 or 2 minutes? Yes?
For the basketball problem, how does the dimensionality increase if I want to add in particular defenders?
You put a defender ID.
Right, yeah. So
Yeah.
how does that, because ideally you would think you have K+1 features for each player, but you have to account for the player interaction.
Yeah, so if you want to do that, so there's a few different ways of doing it. If you assume that the defender ID is an additive offset to the behavior, you can just append it as a feature. If you assume that the defender ID has a very different behavior, and that's potentially non-additive, you have to add that as another order in the tensor. Okay, so next lecture we'll talk about embeddings, and one specific one that's very popular